sedikit introduction lah. Okay, Dr. Kohilavani ataupun lagi mudah dikenali bagi Dr. Kohi, dia grad di Unicell dalam Bachelor Sains Matematik dengan Statistik. Kemudian dia sambung Master dan PhD di UKM. Beliau bekerja sebagai pensyarah kontrak di S51 di UKM sehinggalah tahun 2021 dan kemudian masuk ke Universiti Malaya sebagai pensyarah kontrak. Dan segi research expertise, relayer, heat transfer, mathematical modeling, nanofluid, thin film flow dan computational fluid dynamics. So lebih pada fluid mechanics lah kan. Tanpa membuang masa, saya jemputlah Dr. Kohilavani untuk beri penerangan dan pembentangan berkenaan dengan kajian beliau.
Alright, so first of all, thank you so much, Dr. Hilmi, for chairing the session. A very good morning to all of you. My name is Dr. Kohilavani Naganthran, and I'm from Institute of Mathematical Sciences, Universiti Malaya. So I'm proud to say an alumni from UKM, and yeah, I did my master, PhD, my postdoc, and work here as a senior lecturer in UKM. And under the supervision of Professor Rosinda Nazar, okay, I'm proud to say, Prof, because of you, I'm standing here. Thank you for molding me, okay, and I have a little bit of your character, being thorough, be in detail. I'm doing that to my student too. Thank you so much. Today, I'm standing in front of you, okay, to share my knowledge, my recent research on the triple solutions of Carreau thin film flow with thermocapillarity injection over an unsteady stretching sheet. Okay, so recently I did publish some work on thin film, but there's a reason why I choose this work, because I've identified the triple solution where I believe there's a novel contribution there. Okay, I guess I'm the only one who identified triple solution in the field, in the scope of thin film flow. So let us check. So in this presentation, of course, I'll be explaining about the basic concept, of course, boundary layer, thin film flow, thermocapillarity, okay, and then about the Carreau fluid. And then we check into the mathematical model, and then check up on the computational method, obviously before saying, design discussion, the takeaways, and also I would like to take this opportunity to highlight some of the misleading works, okay, that has been published in the field of thin film flow. Basic concepts, boundary layer flow, okay, it has been introduced by Sir Ludwig Prandtl. So the concept of the boundary layer flow implies the flow at high Reynolds number can be divided into two unequal large regions. So one is the outer inviscid flow, where the effect of the viscosity can be neglected, and there is another layer, which is the second layer, that is closer to the surface of the sheet. It is very thin layer, thin boundary layer, where the effect of the viscosity cannot be neglected. Or boundary layer flow is also known as a frictional layer, okay, but people mostly they use the word of boundary layer. So this is the concept. So our scope is within the laminar flow, okay. So the effects of the viscosity and friction are significant and cannot be neglected in this boundary layer flow. All right, so why we need to investigate about laminar boundary layer flow? Why people publish lots of works about the theoretical laminar boundary layer flows? So one, laminar boundary layer flow, it can help to reduce the drag and increase the lift. So normally, when we solve a mathematical model, we always calculate the values of the screen friction coefficient and then the local Nusselt number y. Okay, we calculate that because we want to find when which parameter vary, how the drag can be reduced. Our aim is we want to minimize the screen friction coefficient. And then next, to improve the efficiency, okay, where the laminar flow can improve efficiency in various flow, for example, heat transfer, fluid mixing, and also reduce turbulence and promoting the smooth flow. Our main objective is to sustain the laminar flow. And then next, the laminar boundary layer flow. From investigating the laminar boundary layer flow, it is more predictable behavior and it has a better control. So these two aspects, like the one predictable behavior and also better control. So these two aspects are very important when we are investigating the process of the real world application, like example, industrial processing, such as oil and gas refining, power generation, automotive manufacturing, and so on. Where we can apply the boundary layer. Boundary layer is everywhere, but the scope, they are actually very small. As I told you, it's a very thin boundary layer, right? So the one I showed here in aerospace engineering, biological fluid dynamics, microfluidics, heat transfer, fluid mixing, and industrial processing, actually they are very big scope. So, for example, let me show you a very specific scope of the application of the boundary layer flow. So, for example, you can see most of the time we always solve the mathematical problem, boundary layer flow and heat transfer over a stretching sheet. So, the application this. For example, plastic extrusion line. So this is the extrusion process. Actually, extrusion process, there are several steps. First, here at this part, it has several steps, you know. So our application applies here at the part of the molten polymer when he extruded in this die, and from there we only investigating at this part only, our model. So from there, yeah, so that is the part. So when we investigate, okay, calculating the value of the steam fission and the heat transfer, so from there we can sustain. We need to, that is very important here at this part, because it will enhance or guarantee the quality of the end product. So this extrusion process also, it is divided into two. One, we have hot extrusion. One is the cold extrusion. Hot extrusion, they do it when at the high temperature. The one cold extrusion, the one the material is under the like room temperature. This is the basic classification of it. So I just give you a brief picture about the extrusion process, because many of you, yeah, even me also, previously when I solve the mathematical model, I cannot see the right application. I really cannot see. And then when you be a lecturer, later on you guys, right, be a lecturer, you need to apply for research grant. They, for example, you apply for the FRGS, they will ask for the which sustainable development goals that is related to your research work. So those things is very important, and in order to relate your proposal, your work with it, you need to know the application. So that is why whenever you're doing, yeah, I know that we are doing theoretical works. It is fundamental, but doesn't mean it is not applicable. It is applicable, but not now. Maybe 50 or 100 years after. Okay, but still applicable. Okay, so you guys need to know this application, but not in too detail. Just like this. Maybe in your Viva examination, maybe your examiner might ask. So you can just pinpoint, okay, it is happening somewhere here. Thin film flow over an unsteady setting sheet. So this is the scope of my work, where the application of thin film flow is the coating process. Say this is the coating material, and then there is a roller there, okay, and from here it happens. So next, thermocapillarity. I guess all of you know, okay, the surface tension. So we know we have the water strider. This is the bulk. So how it works on the water through the, you know, the cohesive forces that appears on the surface of the water there. Okay, so when the water molecules interacted with the gas, so through with the cohesive force, so there's a thin layer of water will be formed. So from there, the water strider, it can work. Okay. So what is the relation? What is the importance of investigating the thermocapillarity or the surface tension in the thin film flow? So when the liquid film is subjected to the unsteady stretching sheet, so it actually undergoing the temperature changes. Okay, so and the temperature gradient in the fluid, it can actually create a surface tension gradient, and that lead to the thermocapillarity forces. So these forces actually, it can affect the stability, the pattern of the fluid flow, and leading to the formation of the droplet and other flow patterns. So that's why it is important for us to investigate about the effect of the thermocapillarity, especially in the thin film flow. Next, Carreau fluid model is actually a non-Newtonian fluid model, and there's a 4-parameter model, and it has shear thinning. Shear thinning means when the viscosity will decreases when the shear rate increases. And then the specialty of this Carreau fluid makes it suitable to describing the wide range of coating fluids, okay, with different rheological properties. And yes, it gained a wider acceptance in industrial and technical flows. Mathematical model is a schematic diagram of my problem. So here, this is a slit. Okay, you just imagine at this part, the coating material in the form of liquid is actually traveling from left to right. So this thing, actually, this is a liquid film. So this is the thickness. Okay, this is the thickness, and then this is the sheet, and it is stretching. It is stretching constantly, and then yeah. So this is the free surface here. So we assume that the film, okay, actually free from any wave. So this is the mathematical model. This is in the form of partial differential equation, but this is already non-dimensionalized. And this is the boundary condition. Okay, the sheet is stretching, and then it has the mass transfer parameter where the sheet is permeable. The sheet is permeable. Please be reminded that there's a difference between the permeability and the porous. Some of the, I think even many paper they are published, they're admitting the sheet actually is porous. Porous means like it can, like a sponge, and then it can go through. But the thing is, if you see here, my model here, the sheet is permeable. The sheet is permeable, and the fluid cannot penetrate the sheet. Cannot. You just imagine there is a paper, there's a paper, and then you put one drop of water, then what will happen? It will absorb, right? So like that, it won't penetrate. So please be careful when you use the term of permeable and also porous. Porous medium, yes, you are right. But for the sheet, permeable. I know some people, they publish using porous. Maybe they want to reduce the similarity index, right? All right. So here we impose the thermocapillarity effect at the free surface, and here we have the surface tension at the temperature, and then the T naught is the slip temperature. And here between the temperatures, so the range of the temperatures are 0, 0, 0, T ref. This is the T, the slip temperature. So we obviously we need to solve our model. Our model now is in the form of partial differential equation. Now we need to solve it. So we need to transform first. Okay, how to transform it? Use the symmetric transformation. I adapt from Wong 2006. Why I adapt? Because his schematic diagram, the geometry is similar to mine. Actually, there is a way for you to come up with the symmetric transformation. You need to do the scaling, the Lie group, or the scaling transformation. But that one is there's another part lah. So you can simply adapt the symmetric transformation used by other paper, other work, if and only if it tallies with your geometry. So it can reduce. So this is the reduced form of the ordinary differential equation. So if you see n is the power law index. So WE is the Weissenberg number, J is the unknown parameter. You know what's the unknown parameter? Is the unknown parameter actually reflects the thickness of the fluid. And then here we have the unsteadiness parameter, and then we have the plunder. Regarding the unknown parameter, you see, as I vary the governing parameters, the value of the governing parameters, the thickness of the fluid will vary, will change. So that one I need to calculate as a part of the problem. But don't worry, BP4C, it can help us to calculate the unknown parameter. So here, the boundary condition, we have the suction injection effect on the surface, at the surface of the sheet, and then we have the thermocapillarity effect, okay, at the free surface. So this also is very important, the physical quantities, the skin friction coefficient, okay, the local Nusselt number. So this is, we call it as the reduced skin friction coefficient, and then this is the local Nusselt number. Computation method, I employ the BP4C method. So it's a building method, and this method actually combined shooting technique and also a direct discretization method. So this is actually quite a robust method. And it is a finite difference method, and then it's also has a collocation polynomial that provides a C1 continuous solution that is fourth order accuracy. In order for you to get the solution, you have to provide a good guess value. You see? Since it is an iteration scheme, effectiveness will ultimately rely on your ability to provide an algorithm with an initial guess for a solution. I know it's very difficult. It is very difficult, especially when you're working with a non-linear fluid and rotating flow. It's very difficult, even to identify the first solution. But actually, coming out with a guess value is a skill. It's a skill. You will take some time to come up with it. So keep trying. So when we start with the BP40 function, so first of all, you need to put your equation into a system of first order equations. So we have it's a third order, right? So you need to put, okay, this is for third order, and then our theta is the second order. So you have to put those things in the first system of first order. So from here, I like my f as y1, f1, y2, and so on, y3, y4 theta, y5, etc. prime. And you just change it to the BP40. So here, the boundary condition will take such a form. So A stands for it describes the position. A means at the surface of the sheet. B means far from the sheet. And then the relative tolerance I set up to 1 times 10 power of negative 10 because I want to match the accuracy with the other work, because most of the work in the field of thin film, last time previously, they work with the analytic method. So just to match my results with them, I used I set the relative tolerance, okay, so that I can compute my numerical solution with a better accuracy. Next, validation. Obviously, when we work with the modelers, when they have come up with the model, they need to validate. Validation is actually very important. So how to validate? You need to reduce some of the governing parameter values to 0. Check it match with which solved problem. If you ask me, it matches with this paper, and then yeah, I can match up to the 3 decimal places. It's okay. Doesn't mean that it need to match 100%. No, because you see, this one he actually used the homotopy method, homotopy analysis method. It is an analytic method. I'm using a approximate method. So actually, find difference method. Somehow, if you can match up to 3 decimal places, it's fine. It's fine. And then here, I also did when I set up like up to these governing parameters, I can match with the problem solved by Dr. Fadia. So somehow I can validate my model. So let's say you are solving a model, but when you choose to set up, try to reduce, make some of the governing parameters up to 0, but you still cannot match with the previous published works, it's okay. What you can do is, but you still need to validate. Doesn't mean you cannot validate. You need to validate. What you need to do is, you can solve that model using your method. Still acceptable. And at the same time, it's sort of you also validating your method. The results. So when the unsteadiness parameter increases, the velocity increases. So don't get confused. Okay, actually the first solution is the stable solution, and the second solution, third solution, they are actually unstable. How I can say it is unstable or not reliable without doing the safety analysis? Let me show you here. Based on the values of the film thickness. So as you can see, when I increase the unsteadiness parameter, the first solution, the thickness actually reduces, which is good. In the real world application, they want to reduce the film thickness. But if you see, for the second solution and the third solution, I got the film thickness negative. So what does it mean? When I got a negative value, the thickness, it means that the edge of the film here, this part already touched the surface of the sheet where the coating process has been disrupted. So why I still present that result? Because I want to show people in the industry there are chances to that thing happen. So that is the role of us. We are the theoretical. We work with the theoretical models. We have the capability to run the simulation and give as much of possibilities to the people in the industry. So whenever you got such a result, don't hesitate to present it. At that time when I worked with Prof. Linda and also with Prof. Lisa, initially they told better don't hide the results of the third solution because it'd be troublesome. Yes, the reviewer asked. They asked, how come you say that the thin film process has been disrupted? Yes, there is and finally I found there's a book, the one explaining that actually when the film thickness become negative, it actually reflects that the edge of the sheet here, of the film here, the liquid film already touched the surface of the sheet. It seems that the effect of the unsteadiness parameter, where it is more than 0, means the stretching sheet being escalated. So when we escalate the stretching sheet, we can see that the film thickness reduced, which is good, and then the screen friction also reduced. Okay, but here the negative signs are actually conveying for the screen friction coefficient. It is conveying that stretching shade imposing the drag force towards the fluid. When it is positive, the vice versa. The same thing goes to the heat transfer. So I think when you analyze the behavior, okay, of the physical quantities, you can take it in a modulus. So it is reducing, which is good. The rate of heat transfer is somehow it is reduced. This is the effect of the thermocapillarity parameter. Okay, actually, there is a significant difference here. Okay, but as the second solution, it has a wider range, so it becomes smaller. So when we increase the thermocapillarity parameter, it seems doesn't favor much into the film thickness because it increases the film thickness. And then for the screen friction, it increases the drag force. Okay, it goes on the shade, and also it also increases the rate of heat transfer. Meanwhile, for the case of the injection, okay, as the intensity of the injection increases, the film thickness reduces. Okay, the film thickness reduces, and the screen friction coefficient increases, the drag force increases, and then the rate of heat transfer reduces. Okay, so you might ask me why I did not consider the suction. Okay, because for the suction, I couldn't identify the second and also the third solution. Yeah, it was quite difficult. So I just present all the values of the parameter where I can get the triple solution. The takeaway. So for the first time up to now, I guess no one presented the triple solution in the field of triple flow, so we did. However, only first solution we call it physically reliable, and the second and third solution are not reliable because with the negative film thickness. Because when we got the negative film thickness, it means that the coating, right, the liquid film already touched the surface. And the increase in the unsteady parameter, higher intensity of injection, it reduces the film thickness, and then it increases the friction coefficient, improve the rate of heat transfer, and then the thermocapillarity is found to increase the film thickness and reduces the skin friction coefficient and reduces the rate of heat transfer. So this is very important for the material manufacturing and material processing, especially in the coating. Here's my references. Later I'll be sharing the slide to you guys. So last but not least, the misleadings. I would like to pinpoint the misleadings in the thin film flow. This is a paper published in Elsevier, Computers and Mathematics with Applications. So this is the only paper where they investigate the thin film flow over a shrinking sheet. Okay, initially when I start to work with the thin film flow, I wonder why people don't work with the sheet. When I just look into this paper, I say no, I don't want to work with the shrinking sheet because we know shrinking sheet B less than 0, shrinking, right? B more than 0, this is stretching, right? All right. So when it comes to the symmetric transformation, the stream function, we have B there, and then the B is square root. So when B is less than 0, does it work? Then imaginary. Something to ponder. I don't know. In fact, I did pinpoint about, I did criticize politely this paper in my recent work as an approximate. Yeah. So you guys, postgraduate students, please don't follow 100%. Published work doesn't mean they are right. You need to check twice. Even though published in Elsevier, so what? You need to be very careful. Check twice, check back with your supervisor. Next paper. Oh, this is very sad paper. Published last year in this journal, okay, Journal of Nanophysics, very reputable. They made several mistakes, got typo in the mathematical model. Well, also never mind, I think acceptable. Okay, I can say they're typo. But I told you, thin film flow days will be one unknown parameter that reflects the dimensionless film thickness. You have to calculate it as a part of the problem. And this paper, they give a value for it. You see, they give a value for it and they produce it. It is very difficult because when there is an unknown parameter, you need to provide a guess value for the unknown parameter also, Maybe they found difficulty. Now my FIP student, okay, actually already work out with this paper. Okay, and we are actually we are planning to publish this work by condemning this. Yes, actually I feel it is actually quite frustrating because these type of works will mislead the upcoming researchers in the field of boundary layer. So I need to do something as a researcher in this boundary layer. I need to do something to correct this. And I don't know how they. Oh, it's a reputable journal. That's why I'm telling you, don't trust the journal. Double check. Okay, guys, thank you. Any question?
Question from me.
Yeah.
In reality, what happened with the coating, as you say, if the coating touches the coating, what will happen if there?
If we disrupt the coating process, so maybe the industry people, they need to stop the process, check what is the problem, and so on.
But if there's no, there's nothing happen or it works normally, so it means that the approximation your is not correct.
Yeah, no, I won't say that my approximation is incorrect, but in reality, there are possibilities for more than one situation to be happen. As you know, when you do one experimental work, you cannot say that 100% it will happen correctly. And when you think, okay, in a company, in a big industry, sometimes, okay, there might be disruption in some part of the process, of the maybe the technical part.
Is it possible to find the possibility of happening this kind of disruption?
That one I need to collaborate with the people in the industry. Yes, then only I can see very clearly. Because now I'm standing here from the theoretical part. Yes, possible, but I need to collaborate with them.
Jadi kita nak tahu that kita sepatutnya for that problem ada third solution atau lebih daripada dua lah. Satu. Just in case kita tahu that third solution tu ada, so maksudnya dekat B4C tu kita kena add another code untuk third branch. Is it?
Yeah. Okay, so untuk soalan pertama tu, kita tengok order kita punya problem tu. Biasanya kalau code order boleh lah, third order pun boleh. Ada dapat, okay? So the second question tu, you can modify your code accordingly. Kalau saya tambah branch lah. You guna branch kan? Saya guna branch. So saya record 3 branch.
Previously you said about suction is not suitable for this problem, right?
No, I didn't say it's not suitable. Okay?
It doesn't show.
I purposely didn't investigate that because with the suction, I couldn't identify triple solutions. Only until dual solution.
So how do you recognize that by adding suction, it doesn't give the third solution? Like it doesn't show the indicator on showing.
By try and error.
Try and error still.
Yeah, try and error basis.
So usually it shows like the red color arrow, is it, or the yellow one? That's a different.
One is red, another one like magenta, is it like orange?
Orange right there.
Yeah.
So both have been on when you put a third solution, is it?
No. When I got my second solution, third solution, when I run, in my command window, there's no such thing, red color and orange color. If you got the red color and orange color, don't take the solution. It is inaccurate. Are you taking that?
No.
Don't. Yeah.
This question because some of the parameter, right, we don't know is it suitable for this problem or not. So I'm just checking what is the indicator that's saying that suction is not very good.
Okay. Suitable. What do you mean by suitable? The parameter suitable to the model. What do you mean?
So I have one problem previously. I unable to obtain the stability for this problem. Seems like I need to add lambda misconvection. So that is one of the indicator that. So I want to check like how do we check whether it's actually need to add some equation or some generic method.
Can you get the second solution for it?
The second solution is unable to get.
You are unable to get.
Yeah, without a misconvection.
How about the flammability? Where it's flammable and shrinking, can you get the second solution? Then why you want to consider the misconvection?
Because at time, I'm focusing on when stability. I'm focusing on MHD, the effect of MHD. When I did neglect the misconvection, because I want to make it a little bit different from the previous paper.
Okay.
Then it shows that the stability unable to get, like it still keep on erroring. Something like
The
that.
stability or the second solution?
Stability.
The stability.
So my question is, how do we check either it's actually need to add or no need to add?
Need to add what? Oh, you mean that the effect?
Yes.
Okay, let's say. Actually, when we start to consider the effects in one model, okay, actually you need to go back to your application, your real world application. It is not that you Simply one model got 10 effects, 20 effects. You're not playing. You're not doing exercise. You're not doing exercise. If you do it now, later you will suffer because you write research grant. They'll ask you to relate with real world application. So you need to go back to your application, find is there any real world application like that, and from there, oh, got application. Then only you start to do it. Sometimes maybe it may not be logical. That's why it doesn't turn out. And then choose the right value of the parameters. That was also very important. You have to use the right value of the parameters. And actually, we can find the second solution. We can find the solutions, but you need to use the right value of the parameter, and then the boundary layer thickness, and then you need to put more effort. Actually, there is a paper. They sort of giving guidance on how to form the gas values. However, it doesn't work. When you work with the non-linear fields, I know the Prof. Ida knows there's one paper. 1 year I cannot solve. Then I can solve when I impose the suction injection. So normally the visibility of the second solution, you can, based on my experience, you can impose the suction injection. Next, any questions?
What is the main difference between non-Newtonian and Newtonian?
Okay, dia punya
Correlation.
dia punya viscosity lah. Dia punya coefficient kalau Newtonian dia kan linear. Kalau non-Newtonian is non-linear. Non-Newtonian pun ada banyak jenis. Viscoelastic, elastic, shear thickening, pseudoplastic.
One thing about Dr. Kohi, dia sangat dia suka nak relatekan dengan ni lah, real life application, because I think she got that kan. She need to do that.
Yeah,
and macam you kata you nak apply grant ke apa
yes,
kan,
some
people
more,
will ask that.
Some more in Universiti Malaya, semua grant memang ada grant opportunity, and they also visit the 10 Malaysian starts to
even FRGS now also semua nak kena ada nampak application tu lah.
And then kat sana kita rasa macam tak secure because orang lain boleh dapat, engineer ni buat dapat, kita orang theoretical ni. So you need to come out from the comfort zone. Yeah,
So kita we call ourselves so-called applied mathematician. Kalau kita memang betul-betul pure mathematician tu orang tak boleh nak pertikaikan, memang kita buat all these theories and tapi bila kita kata kita applied mathematician, orang nak nampak application. Tak boleh nak kata we are applied mathematician tapi kita solve just theory. Tapi you nak apply all this sort of research grant yang memang orang akan tanya application. Kena ada dulu boleh lah. I think masa zaman saya buat PhD dulu macam kita memang kita kata kita applied mathematician yang memang kita solve ni model aja, kita tak nak ambil tahu sangat tentang application. Tapi sekarang banyak benda kita boleh explain because kita tahu, kita faham benda tu. Macam Dr. Kohi, I think she is getting better and better in that sense lah. Getting better than me pun.
Tapi make sure lah kalau dapat examiner bidang lain, watch out. Sebab saya dapat my pre-viva Dr. Azmi. She's from biomechanics. So she asked, you apa ni? Semua problem dapat second solution and you got stability, stable, unstable. So what? You have to be very careful. That's why I cakap physical tu. So nak touch physical tu, you have to know the application. Itu yang penting tu. Application tu memang ada. Impossible tak ada application. Kalau tak macam mana sampai sekarang ada boundary layer. Proses ni betul. Sah, baik. And satu lagi bahaya mungkin lah orang bidang lain they might don't like lah. So kita kan cepat publish and so on. Actually matematik social tu memang suka. Bukan tak senang, suka ya.
Dan sekarang banyaknya terkandas di review. Bila you cannot really explain it. Saya tengoklah kalau paper banyak review yang macam major revision tu sebenarnya banyak. The reviewers are engineers, machines. They will ask all these sort of things and then dia tengok kita pusing-pusing, itu juga kita jawab balik kan. Kita tak try to explain kan. So itu dia lah, dia kata okay, mula-mula major adalah reject. So saya macam, so you should be able to explain lah. I think dulu boleh lagi kot masa tak sangat kompetitif kan. Sekarang ni getting more kompetitif lah, kita dah ramai sangat orang submit papers kan. Jadi dia kena ada dia punya success rate tu, setiap jurnal ada dia punya success rate dia. Jadi dia akan tengok the way kita reply kepada reviewers.
Berkenaan dengan validation, So sebenarnya validation ni yang paling terbaik sebenarnya kita compare dengan apa yang guna method lain ke ataupun method sama dengan kita.
Method yang dia guna method lain.
Contoh kalau saya guna BBOC, maksudnya lebih terbaik dengan method lain lah.
Guna method.
Tapi kalau compare dengan method yang sama, tak ada masalah juga ke?
Tak ada masalah. Jika situasi dah macam tu,
Tak ada lah, tak ada paper yang
ya,
kan?
ya.
Boleh.
Saya pernah sampai model tu memang online, saya tak boleh reduce from. Tak boleh. So saya ambil paper itu, saya solve guna BP positif. Tapi dia guna method lain. Dia boleh publish.
Yang kedua, pasal coding.
Coding, bukan coding.
Coding.
Dua coding.
Ya.
Dua coding.
Ah.
Coding tapi tak ada dalam coding, tak tahu lah.
Saya terpujuk lah.
Bukan. Dalam saya punya problem, mungkin Dr. Anwar pernah tanya kot pasal Unsteady kot. Dalam tu ada eta.
Okay,
Dalam
okay.
kita punya wiki tu
Yes,
kan.
yes, yes.
Cuma bila saya solve problem tu, saya tak boleh nak keluarkan generate eta punya tu.
Data tu kena letak X.
Saya dah cuba, dia keluarkan.
Kod area yang macam dia
Dia
kata,
column.
vector column tak cukup.
You kena semak vector column untuk mungkin lah dekat you punya ODE atau dekat boundary condition. Dia ada yang tak tally. Okay, let's say lah you ada 5 boundary condition. So row tu dia kena 5, 5, 5. Like, biasanya 5, boundary condition 5, dekat ODE pun 5. So ada satu je yang dia tak tally lah. So you have to check back.
Maksudnya dia tak kira tu bila dia masuk nilai ke atau
Bukan sebelum masuk nilai tu. Dia memang before you masuk nilai tu. Dia tak tally.
macam dekat ODE.
ODE, boundary condition, dan sebagainya. Maybe saya boleh tengokkan after this.
Boleh. Bagi saya soalan halaman.
Satu lagi.
Pasal tiga tu.
Satu lagi relative tolerance tu. Macam kita orang kebiasaannya guna 1 kali 10 negatif 5 lah. Dia sebenarnya boleh lebih dengan kurang.
Boleh lebih daripada kurang. Kalau you tak set, MATLAB guna yang default punya 1 times 10 negatif 3. Tapi result dia tak begitu accurate lah. Sebab orang lain kalau guna method lain, dia takut accuracy lebih tinggi. So you can use negative 5. Saya masuk time PhD guna negative 5. Lepas postdoc semua sudah increase dah negative 5. Ya. Tapi you just, you can set negative 5 to negative 10. Dia memang tak affect lah. You cari the second solution, the solution.
Dia antara negatif 5 dengan negatif 10 je. Yang kalau kan sebelum ni MATLAB defaultly adalah negatif 3. So better check between negative 5 and negative 10, is it?
Ya, boleh juga. Dia ada limit juga, but I don't remember lah. I think negative 10 is enough.
Okay, last question. Berkenaan dengan stability analysis, Dr. Koi dia menggunakan berdasarkan J.
Tak, untuk ni saya tak buat stability analysis.
Tak buat.
Sebab saya memang tak membangunkan contribution code untuk problem ni. Sebab dia ada unknown parameter, satu unknown parameter. So I need to alter something with the gas value. So sorry, with the contribution code, kena alter tau. Sebab dia punya code ni sedikit berbeza dengan what you guys do. Sedikit berbeza. Because I have the unknown parameter. Yes. So far memang stability belum lagi. Dah jadi tengok prof.
Juga.
Kalau ada tu contribution baru lah.
Ya, kalau dah buat tu, ya, itu dia.
Ada orang buat lagi.
Ada lagi soalan ke?
Saya nak tanyakan, Mas, kalau kita buat problem non-Newtonian, lepas tu kita punya F kita highest dia F double prime je. Dia tak ada triple. Double prime. Random Pelipov. Random Pelipov. So, dia ada F double prime je, dia tak ada triple. So, masa boundary condition tu kita nak rest kan, masa buat stability kan kita nak rest kan salah satu boundary condition.
One of the outer boundary condition. One of the outer boundary condition.
Okay, betul. So, biasanya lah kita kan restkan F prime kan dan digantikan dengan F double prime kan.
Yes.
So, macam mana kalau I punya highest F tadi, F double prime. So, masa kita nak ganti tu, kita ganti dengan equation ke?
Actually, you boleh ambil theta juga. Tak semestinya you perlu ambil the F. Any of the outer boundary condition.
Oh, okay.
Okay. So, in your case, you have to take the temperature. Understand? Sebab bila you introduce the first order yang variable tu, so
contohlah bila I tu follow paper lah. Bila kita read paper before semua dia replace dengan F double prime. So kalau I tukar kepada F kepada H ke boleh lah.
Boleh. Okay, thank you so much for your attention.
Okay. So sekali lagi saya cakap terima kasihlah kepada Dr. Kohi sebab sudi datang ke UKM daripada UM Putu. Okay, itu saja untuk hari ini. Terima kasih.